This week's seminar. We are very thrilled to have Rafael here. And as you noticed, we also are in a different room, but I think we did manage to get everything working and set up. So Rafael Martinez Galarza's research focuses on multi-wavelength studies of star-forming galaxies, as well as on the use of machine learning techniques for the exploration of large astronomical data sets, specifically with the aim of finding astrophysical transients such as X-ray binaries or tidal disruption events. Rafa received his PhD in astronomy from Leiden University in the Netherlands in 2012. He was a postdoctoral fellow at the CfA and a teaching fellow at Harvard's Institute for Applied Computational Science, where he taught stochastic optimization and machine learning. Until September of last year, 2024, he served as the deputy end-to-end scientist for the Chandra X-ray Center Data Systems and is now the deputy director of Astro-AI. He has also worked as a calibration scientist for the mid-infrared instrument of JWST and is currently a member of the LSST Science Collaboration in Transients and Variable Stars. And today, Rafa will talk to us about representation, self-supervised learning for discovery of high-energy astrophysics.
Thank you, thank you, Ole, and thank you to Costadina and Ole and Julia and Federico for organizing this. The good news about doing it in this room is that it actually looks like there's an audience. In the Philips auditorium, always people look a little bit spread. As Ole just said, I am unfortunately not part of the CXC anymore, but a lot of what I'm going to be probably telling you about today has to do with Chandra X-ray datasets. Fortunately, however, I am still at the CfA as part of Astro-AI, and what I'm going to tell you about today is about machine learning, in particular about a particular aspect of machine learning called representation learning and self-supervised learning. And I hope that regardless of what your opinion is about machine learning, you might be convinced at the end of the talk that it might be useful for some tasks in astronomy, in particular in discovering interesting sources. Okay, so I'm gonna get started. And I always like to start these talks with this object that was discovered already 6 years ago, GSN 069. It was serendipitously discovered while XMM Newton was doing a slewing from one observation to the other. And what's interesting about this object is that if you look at it in X-rays, it has these flashes that repeat every few hours. And I like it very much because it was a serendipitous discovery that resulted in sort of a new field and new avenues for research in high energy astrophysics. Because people originally did not know what these quasi-periodic eruptions were. And so a number of theories had to be brought up in order to explain what was causing these flashes in X-ray emission at the center of this galaxy at redshift of 0.01. And what could be causing this? Things like mass transfer from a tidal disruption event, or even gravitational lensing that would produce this regular pattern, or maybe something else. In fact, I think one of the theories that I like the most, that I think it's also what among the experts here is more plausible, is perhaps the presence of another compact object orbiting the accretion disk from the tidal disruption event around the supermassive black hole and intercepting the disk every certain amount of time, producing those very soft thermal emission flashes. So I like to start with this object because I think it's interesting to see that there's serendipitous findings in astronomy very often. And even though we as X-ray astronomers may be thinking that we are not necessarily a big data crowd, there is now a fertile ground for discovery in archival data, in Chandra, XMM Newton, Rosita, et cetera, And the question is, how do we profit from this fertile ground for discovery, and what sort of tools can we use in order to to make this serendipitous discovery a little bit more systematic? And I am going to argue that perhaps machine learning is such tool that could enable those things. And there's at least, I think, 3 reasons why that is the case. One is, well, X-rays X-ray datasets are in fact growing. We have more and more catalogs, millions of sources so far detected in the sky, with lots of properties, spectral, time domain, etc., etc. And these datasets continue growing. There is still, as I said, a lot of, I'm gonna say low-hanging fruit here and there in the archives of X-ray astronomy archives that sort of motivate the use of novel ways of looking at the data in order to make more discoveries. And then there's also something more pragmatical, which is, for example, the treatment of nonlinear effects in X-ray detectors and how methods of statistical learning can help in mitigating those effects when we calibrate instruments. And that's why I think we should at least explore the possibility that we should use machine learning. And it's not just me. I think very rapidly the X-ray community is starting to realize this. And there's been a number of publications in the last couple of years about the use of machine learning in X-ray astrophysics for classification, for inference, for anomaly detection. And I certainly encourage you to review some of the literature on these topics. And now we're lucky, and we're particularly lucky here because we have the Chandra Source Catalog, which I would say is kind of the crown jewel of the data archive of Chandra, which is the collection of all the sources that have been detected with the Chandra X-ray Observatory. And it's been recently updated to version 2.1, where the coverage of the sky has been increased. And we have of the over 400,000 sources in the sky, individual sources in the sky that have been fully characterized as part of the production of the Chandra Source Catalog. We cover a significant fraction of the sky. We used all of the Chandra observations all the way to the end of 2021. We have better astrometry now in the catalog because we have tied the reference frames of the Chandra Source Catalog to the Gaia reference frame, and that has improved in multi-wavelength tasks because you can now better cross-match your Chandra Source Catalog sources with sources from other surveys. For example, with SDSS and with spectral surveys from SDSS. So it's a great tool for exploration. And I want to show you a few examples of how that exploration can be done in order to promote discovery. And with regards to the data science aspects of exploring the Chandra Source Catalog, I think it's a great data set because each of those X-ray detections in the sky is basically a collection of individual photon detections, a list of photon detections with arrival times, energy. And from those detections, you can build the things that you're interested in. You can build images, just if you've been those events spatially. You can also build light curves if you've been them in time, or spectra if you've been them in energy. But ultimately, all the information that we infer about astrophysical sources comes from that collection of photons. So it's worth thinking, well, how can we exploit automatic systems to explore the information that is contained in the individual photon events, and the catalog provides not only the photon events, but all the astrophysically relevant quantities that are derived from those events. So it's a good way to have some sort of training data set on which you can try things and have some targets quantities. Oh my gosh, sorry.
I told you every 5 minutes.
Yes, thank you. I forget that I need to move this. She had warned me, but I forgot. Anyway, so what sort of interesting science or what kind of interesting objects can we find in this catalog? I think I want to make the case for time domain astronomy in high energy astrophysics. There's a number of objects of interest that have been identified in catalogs like the Chandra Source Catalog. And if you're interested, for example, in gravitational wave science and in multi-messenger, then an interesting connection has to do with binary neutron star mergers, where a very particular type of transient, the fast X-ray transient, can result from the merger of two neutron stars when the end result of the merger is a rapidly spinning magnetar, because the opening angle of the X-ray afterglow is larger in general than the opening angle of the gamma ray burst that results from that merger, and so you can have more viewing angles at which you can detect these objects depending exactly on where you look. That magnetar, you have different types of light curves, and people have been looking for these fast X-ray transients in catalogs, including the Chandra Source Catalog. And I want to point out to the work of Quirola Vázquez and collaborators who've done a lot of work on sort of automatic non-machine learning methodologies to finding these flares with great success, and also characterizing the shape of the light curve and seeing whether the shape of the light curve is consistent with the spin down of the magnetar, the thermal emission coming from this event. So that's one thing that motivates, these kind of searches. There's also things like type 1 X-ray bursts, which are basically runaway thermonuclear explosions in the surfaces of neutron stars. These are kind of the equivalent to classical nova, but not on white dwarfs, but on neutron stars. And they also present themselves as transient phenomena. And depending on what sort of material is being accreted, how much helium versus hydrogen there is, etc., the light curves might look different. And the search for these sort of objects is important. Most of the about 100 objects of this type have been identified in the Milky Way. So these are just two examples of things that you can find. And the question becomes like, how do we use methods of machine learning and statistical learning to find them and to make this a little bit more interesting, or to augment the amount of information that we can get from these event files for the purposes of discovery. And so that's where the representation learning kicks in. And I want to give you a few examples of how this can be used for this type of discoveries. So I'm gonna introduce what I mean by self-supervised learning. Self-supervised learning is a type of machine learning where you don't need a human to previously assign labels to the objects that you are going to target in your search, either for classification or for regression. In self-supervised learning, you sort of learn directly from the data. And the way to do that is by having a system, usually a deep neural network, right? That is just a combination of vector operations between your data and some weights, and then you modify that with a nonlinear function after that. But that's just a system that is trying to approximate a function. And you can train it for some sort of task. So for example, if you have images, you can train a neural network to predict what the rotation angle of the image is if you present the neural network with the same image but rotated. And in order to do that, the neural network would create sort of a representation, a bottleneck. It will create a lower dimensionality version of your data that contains relevant information for that task. But it turns out that if you choose that task cleverly, you can then take that low dimensional representation of the data and then use it for other downstream tasks on which the neural network had not been trained. So for example, you can now take those representations that were not trained on the task of classifying the type of the image, and you can now use them as the features of a classifier. So you can now use those representations that were extracted for the data for a particular task as the inputs to other systems that will perform a different task. And usually, if you've done this correctly, those features will be much more informative for that task than manually extracted features that humans would normally think of. So for example, in this case, you can then take these features and train them for classification, and then use your features as the inputs of a classifier that will tell you if the image is a dog or a cat or a galaxy or whatever. So one very famous example of self-supervised learning are, of course, large language models. And large language models are trained on the pretext task of predicting the next word or the next character in a phrase. So if you see this phrase, you might be able to maybe predict what the next word is, because you're very clever humans. But that's what large language models do. And then the representations that these large language models create of language can be useful for other classification tasks, like to classify text according to the topic, etc., etc. So that's what self-supervised representation learning means. How can we exploit this for X-ray astronomy? So this is an example of a project with a student, Steven Dillman, who tried to use this precisely to discover transients in X-ray datasets. And the way he did this was by using this system that is a couple of neural networks, right? One is called an encoder. This is a decoder, so this is called an autodecoder. And this system is trained to reproduce an input. exactly as the output of the system by first reducing the dimensionality and then expanding with another neural network in order to try to reconstruct exactly the input image. So you condition the neural network to try to condense the information from this input into this smaller space so that you can still recover the relevant information about the system. And in this case, these entries are just two-dimensional histograms of time and energy of the photons that were recorded in the Chandra observation, for example. So Stephen worked on this system and he wrote a nice paper where he took the Chandra source catalog event files, he created those representations, and then just as I just described, he used those representations as the input of a neural network, an autoencoding neural network, and then took that bottleneck low dimensional representation and projected it into 2 dimensions, right? And started looking whether these interesting objects that I was describing at the beginning of the talk were located somewhere in that representation spaces. And as a matter of fact, those interesting, flares and fast X-ray transients, and even transits in dipping light curves were all sort of living in some islands in this representation space. So that meant he could exploit the system to find other candidates that probably lived in those regions as well of the representation space. So we transformed the problem into a look at this map and look for islands that might contain interesting objects, because all the objects that live in this island behave similarly. And by doing that, he was able to discover an interesting object. This is, we believe, the most likely explanation for this object is one of those type 1 bursts on the surface of a neutron star. If that's the case, is one of the few that has been identified outside of the Milky Way. This is in particular in the direction of the Magellanic Cloud. If it's in fact in the Magellanic Cloud, this is about the luminosity it has. And this is an interesting fast X-ray transient because it's harder than the usual soft transients that are associated with either tidal disruption events or things like binary neutron mergers. So this is an interesting example of how you can exploit this system to find interesting new transients. You can read the paper. There's also a nice Chandra blog post that he wrote about this particular discovery. And this is only one of the examples of things that you can discover using other objects. So these other things, hyperluminous, super soft, it should be super soft there, sorry, X-ray sources. These are hyperluminous, these are luminosities larger than 10 to the 41 hertz per second. They're also extremely soft. Tidal disruption events are the prime example of those things. And this is work, by the way, by Andrea Sacchi. Oh, sorry, I got the wrong Andrea Sacchi there. It's not the Italian Baroque painter. It's actually our own postdoc here who happens to have a namesake in Baroque Italy. But anyway, he was looking for these super soft sources, super luminous sources in the Chandra source catalog. And he combined both. He combined both a classical search by performing certain cuts on the luminosities and on the hardness ratios of these objects. But he also looked at that representation that Stephen had created for finding transients. And he in fact discovered that the majority of previously identified hyperluminous X-ray sources, super soft X-ray sources, were living in very specific locations of this representation map. And he confirmed that one that he discovered, this object here, J1035, was also in that location. So he's using this, yes, to do that. Anyway, so it looks like I need to hurry up. But anyway, this is an interesting example of how you can also find other types of transients. Now, you don't need to, Stephen's representation is only one way to look at Poisson-like arrivals of photons. Another student, Harvard statistician Jan Kesson, worked on this other system that, again, I'm not going to go into the details, but this is another neural network. And the pretext task here is to reconstruct the light curve. So you have a bunch of event files, and you enter those event files to a neural network that will try to predict what is the most likely time varying Poisson rate of the process of detection. So it sort of reconstructs the light curve at any given energy. So you can do the soft light curve or the hard light curve. And in the process, you also create a latent representation that is a low dimensionality representation of your data. And those representations turn out encode information about hardness ratios of the source. They encode information about variability. So some islands would correspond to the highly variable objects. And they can be exploited for things like nearest neighbors anomaly detection. So if you're interested in objects that have a soft light curve, this is soft, medium, and hard, that soft light curve that has dips, then you can look for the nearest neighbors in this representation of the data and find other objects that also have dipping behaviors in the soft light curve. And that's a way to exploit another way of exploiting. And these representations are also good in tasks of classification, for example, comparable to classifiers that use, for example, the properties directly computed as part of the Chandra source catalog. So you don't need to compute things like the hardness ratio or the variability index. You can just take these representations and use them as the inputs for classifiers that can help you do this classification work a little bit better. I want to show you the last thing, and that's something I've been very interested in lately, which is combining these representations from X-ray data sets with large language models. As I mentioned before, large language models also create representations. So those are representations of text. And then there is a technique in machine learning called contrastive learning. And contrastive learning will try to pair representations in two different modalities, right? And try to place representations that come from the same, that describe the same object close in a shared representation space, close together if they come from the same object, and far apart if they are coming from different objects. So if you have a collection of X-ray sources and you have a collection of text describing those objects, you can try to represent them in a single space and then look for neighbors, regardless of whether your data came from an X-ray event or from a description, a textual description of that object. This is called contrastive learning. And we've exploited the Chandra data archive here. The Chandra data archive did a very important thing, which was pairing obsides from the Chandra X-ray Observatory with papers. So we could make a pairing there, right? And we're also exploiting the fact that we have ADS here, and so we have access to some of the text. And we use Simbat to create pairings between sources and test description of those sources. Why is this important? Because once you train this additional neural network that will do this and put things that are similar together, then you can do similarity searches for objects. So you could think of an object that you're an X-ray astronomer and you know nothing, or you're not an X-ray astronomer, you know nothing about event files, but you're given an event file. You say, these are the photos detected for this particular source. And I am going to, I know nothing about this source. So it wouldn't be great to have a system that presents you with some ideas about what this object could be. Because we did this process of aligning the two representation with a large language model representation, we're able to see that the large language model representations encode information over the physical information of the object, for example, the hardness ratio. And by doing this similarity search, we can do things like this. You can do things like given an object that you can encode in a particular location of this mutual shared space, what is the closest description for that object? Or can you ask questions about that object to this system that has the aligned representations? And this, because it has shared information between the event files and the accumulated knowledge in the literature, can provide you with an answer. So you provide an event file and you ask, well, I don't know what to do with this. What sort of spectral model can I fit? And the system will return something like that. So we've accomplished a first step of this process that we hope will become a tool where you can interact with the system and present it with actual data rather than words, and then ask questions about the data to get answers about suggestions as to what this data could represent or how it could be fit. And if you're more interested, you can read this paper that was recently accepted for a machine learning conference. It's open review, so it's open to the public. It's just proceeding, so it's still work in progress, but stay tuned for a full deployment of this tool for you guys, the X-ray astronomers, to test on in the near future. Briefly, I want to highlight work by Justina and Ole here, who've been working on a neural network to mitigate the effect of pileup in X-ray detectors. And please stay tuned also for this project that also use a neural network for this. And since I'm running out of time with that, I'm just going to leave it at it. Thank you so much for your attention.
Great, thank you very much. Do we have any questions in the room?
Yeah, I've noticed no one has signed up to speak to me in this question. I am very offended.
But this is my fault because.
No, okay, that was just a joke.
Yes, please.
So do you think expanding to the X-ray data archive, will it add, subtract, or not really change results?
If you do what, sorry?
If you took like the X-Men catalog,
Oh,
you know, I mean, doesn't it, you know, expand some of these things?
yeah.
You know, there's like, when does that more data help or harm?
Yeah. Of course, we want this to be as modular as possible, so you can add other data sets. The systems we have so far, we have trained them on Chandra X-ray sources. There are techniques that allow you to transfer that knowledge to a data set, for example, event files from a different telescope, but it takes another step. Now, that said, it should be possible to expand. You know, all these things are, the more data, the better, in the sense that you have more representations, more expressivity in these representations, and of course, you will want to be able to do this with eRosita and with XMU as well.
Yes.
So in the process of this supervised lesson, the task of finding the lower representation, what exactly does the human have to do?
What does the human have to do? Well, the human still has to validate all these things. So, for example, what I just showed you here, I mean, I read something yesterday on LinkedIn that was very, very interesting. We said, you know, in academia, we're not going to prevent people from using large language models because people are going to use them anyway, but people should be responsible for what they take out of those large language models. And I have to say, I am not declaring myself responsible for this answer at the moment. So I think the human intervention is still needed in validating this thing. So we are going to deploy a system where we will provide the X-ray astronomers who have domain knowledge with a tool to validate whether the things that the LLM extracts by making this alignment make sense for particular specific types of X-ray sources. And that process of validation still relies on human. You've trained it on human knowledge because you've trained it on papers that people wrote, but you still want to make sure that the alignments and everything that you did is correctly, and how much the neural network makes mistakes when it tries to align these representations. So that's a way in which humans can still certainly hold.
There's a lot of information, you know, in the multi-wavelength space. I wonder if anybody is working on, you know, cross-correlating Chandra X-rays, other large data sets and other wavelengths in order to classify things, not just based on the X-rays.
Yeah, I'll take this one and then we can move to Elena's talk. Yeah, so the multimodality is one thing that people are thinking a lot about in X-ray and machine learning and astronomy. So the same way I created a representation of X-ray sources, one representation of text. People are working on creating a representation of a light curve in the optical, and then of an image in the optical, and then align them in the same way so that you can predict things that you usually get only from one of the modalities. For example, the redshift from a spectrum, by just looking at the image of the galaxy. So these things are possible, and we are planning to expand this program to include cross-matched objects that have X-ray counterparts in order to learn more about X-ray sources from their optical or infrared properties. And with that, thanks very much. We have Elena now.
Yeah.